Assalamu alaikum and very good evening to all of you. I hope you had a good day today. In this video, I am going to deliver a comprehensive lecture on quasi-concave and quasi-convex functions. I have already uploaded two videos, one on concave and convex function in case where y is a function of x only, one variable case, and in another video, that is video number 458, I discussed the convexity and concavity in case when z is a function of x and y. That was the two variable case. In this in the present video, I am going to explain quasi-concavity and quasi-convexity using complex mathematical functions. So this is basically meant for advanced level students of MPhil and PhD. My dear students, as you know, convex, concave and other related functions naturally arise in economic theory, and these functions include utility functions, cost function, expenditure function, past function, production function, and so on. Moreover, concavity is usually assumed of utility as it ensures a diminishing minor rate of substitution. It often also applies to production theory or theory of production. Now let me discuss convex and concave functions. Convex and concave functions are only defined when the domain is convex. And what does it mean? A function f such that it is mapped in the domain S into R is convex if for all x and y in S and 0 is less than or equal to lambda is less than or equal to 1, then this function of lambda x1 plus 1 minus lambda x2 is less than or equal to lambda f of x1 plus 1 minus lambda f of x2. So if this condition is met, then that function f is convex. A function f mapping in the domain S into R is concave if for all x, y in S and 0 is less than or equal to lambda is less than or equal to alpha, then the set f of lambda x1 plus 1 minus lambda x2 is greater than or equal to lambda f of x1 plus 1 minus lambda f of x2. When the inequalities are strict, for 0 is less than lambda is less than 1, we say the function is strictly convex or strictly concave. So in case of just convex and concave, the inequality is not strict, but in case of strict convexity and strict concavity, the inequalities will be strict. One of the consequences is that for convex functions, every chord of the graph of function lies on or above the graph. So if you look at this figure, this is convex function. So this line which connects this point with this lies on or above the graph. So this function, this line is above the graph, so this is convex. On the other hand, this is a kind of concave function. Here the chord of the graph of the function lies below this graph. So for concave functions, every chord lies on or above the graph, and on the left panel shows a convex function where every chord connecting any two points of the graph lies above the graph. So this is the left one. For concave functions, every chord lies on or below the graph. So this one is below the graph. So this is the main difference between the two, and this is the simple definition of concave and convex function. The right panel illustrates a concave function and every chord connecting any 2 points of the graph lies below the graph. Now we discuss quasi-concavity and quasi-convexity. Let us recall that convex and concave functions were characterized by whether or not the area above or below their graphs were convex or not. There is another class of functions that are characterized by whether or not their upper or lower contour sets are convex. So this is very important, and I'll discuss this later in this video. So it turns out that for economists, the critical issue about a function is not whether it is convex or concave, but simply whether its upper or lower contour sets are convex or not. This should be very familiar by now to you, and you may recall that what matters about a person's utility function is not the amount of utility that a person receives from the different bundles, but the shape of the person's indifference curve. So the shape of the indifference curve matters more than the quantity of utility derived from a particular bundle. Well, indifference curves are just the level sets, and we may note that we always draw functions that have convex upper contour sets called the law of diminishing marginal rate of substitution. So it means that usually we draw indifference curves in such a way that they are convex to the origin, and that basically indicate that there is diminishing marginal rate of substitution between the two goods as we move from left to right downward. Here is another case of quasi-concave function in this graph. So first we define a function is quasi-concave if all of its upper contour set are convex. It means all this area, which is shaded area, this should be a convex set. So a function is quasi-convex if all of its lower contour sets are convex. In most of the textbooks on microeconomic theory, we find the assumption that utility functions are quasi-concave, and most people find this difficult to understand, although they are quite understandable and easily explainable, and they are used to assume that there is diminishing marginal rate of substitution between these two. So that is why indifference curves are drawn in this way. Another good test of whether you understand quasi-concavity or not is to look at the concept in one dimension. So this is one dimension. Here we measure x variable, and here is y variable, and y is a function of x. Similarly, y is a function of x, so y is dependent variable and x is independent variable in all these three cases. In this figure, there are three types of graphs. The first one is concave, this one is quasi-concave, and this one is not quasi-concave function of one variable. Now let us consider a typical indifference curve U0 as shown in a figure. Let me show you the figure. So this is a typical indifference curve which is shown by U0, and utility is a function of x1 and x2, where this is good 1 and this is good 2. Now we may consider a set and we call it S. So this is S. S is here. This is set S of the points that are at least as preferred as any point on the indifference curve U0. And this is shown by the shaded area. This set has the property that if any 2 points in set are connected by a straight line, the entire line also lies in S. It means that this whole set in the shaded area is convex set. So a set with this property is called convex set, but it should not be confused with a convex function. There is a hell of difference between convex set and convex function. So we are talking here of convex set rather than the convex function. So as an example of the set that is not convex, consider a set of consumption bundles that are less preferred than those on U0. So that will be the set of those points which are below this indifference curve, which are less preferred to U0. Let me also discuss preference relation in relation with the convexity. Preference relation is convex if the upper contour set is convex. We have been discussing this for quite some time, and it means mathematically that for all x in the domain x and the set of y in x such that y is at least as good as x. Thus, a preference relation is convex if for all x in the commodity space, this capital X is known as the commodity space, the upper contour set y in x that is also in commodity space such that y is at least as good as x, and this set is convex because we can see that these 2 points are connected by this line, and this line lies entirely in this set S. So this is convex set, and this is the upper contour set for the convex set. We see in this graph y is at least as good as x, and z is also at least as good, and x where z and z and x are on the same indifference curve, where y lies above this indifference curve. And if we take the linear combination of y and z, where lambda is in the interval 0 and 1, such that lambda y plus 1 minus lambda z is at least as good as x. So any point in between here is also at least as good as x. This is something that utility function is quasi-concave, and we may say that a function u which is mapping from the domain into R and set of x in the commodity space such that utility of x is greater than some given level of utility u bar. So we can define a function u, that is the utility function, is quasi-concave if it is mapping from the domain x into R and the upper contour set is convex, and this means that this is the upper contour set which is convex. Similarly, a utility function, if it is mapping in the domain from the domain x into R and the set of x in x such that u of x is less than or equal to some given level of utility, that is a quasi-convex function. So that is a function, say u mapping from the domain x into R is a quasi-convex function. So this is quasi-convex function. This is not quasi-concave, and this is non-convex upper contour set, looks like this, and that is x in commodity space such that utility of x is less than some given level of utility. For all x in x, capital X, that is commodity space, y, a set of y in x such that u of y is greater than or equal to u of x must be convex. In the below figure, in this figure, the upper contour set consists of those two sets is not convex, because we can speak, I am talking of this figure. In this figure, the upper contour set consists of those 2 points like A and B, and the linear combination of this somewhere in the middle like C, which lies out of the set, and at C the utility of C is less than the utility of X. For example, if this utility will be less than the u of x, so this lies out of the upper contour set, so this is not quasi-concave. Further, we may have utility function as shown in the figure below. We may think of two commodity bundles, x and x prime. This is x and this is x prime. The utility associated with x is u of x, whereas the utility associated with x prime is u of x prime. And let us take a linear combination of x and x prime, and if lambda is 0.5, since this is in the interval 0 and 1, if we assume that lambda is equal to 0.5, then the linear combination of x and x prime will be somewhere in the middle, that is x double prime. So then lambda x plus 1 minus lambda x prime will be equal to x double prime, and the utility associated with this linear combination, that is the x double prime, is equal to u of x double prime, and this is greater than both of these. So the utility of x double prime is equal to u of lambda x plus 1 minus lambda times x prime. In this graph, utility of lambda x plus 1 minus lambda x prime, that is this utility, is greater than lambda u of x plus 1 minus lambda u of x prime, and that would be somewhere in between. So this utility of the linear combination is greater than this statement, that is lambda u of x plus 1 minus lambda u of x prime. So this is the property of a concave function. So as we see, this is a concave function. For a convex function, u of lambda x plus 1 minus lambda x prime will be less than or equal to lambda u of x plus 1 minus lambda u of x prime. So this is the opposite of this. So all concave functions are also quasi-concave. However, the opposite may not be true. That is, a quasi-concave function may not necessarily be concave. Let y be y in the commodity space x such that u of y is greater than or equal to u of x. This would be found in this area in this figure. So this condition will be met here. But we may find any two points like x and x prime, and we could look at the utility of a linear combination of this, then u of y is less than u of x. So this function is not concave, but it is quasi-concave. So this is how quasi-concave look like. It's not a regular concave function, but it is as if it is concave function. So quasi means somewhat like concave or as if concave. Again, let me sum up. We may say that a function is said to be quasi-concave if the set of points for which the function takes on values greater than or equal to some arbitrary amount, say u naught, these points are represented by the shaded area. So that set is a convex set, and such a function is known to be quasi-concave function. So this property is generally assumed for utility function and production function. Let us sum up the entire presentation. So the definition of the concave function is: a function f is concave if for all x and y in the domain, that is in the commodity space, and lambda in the interval of 0 and 1, such that f of 1 minus lambda x plus lambda y is greater than or equal to 1 minus lambda f of x plus lambda f of y. And if and the function f is convex if the inequality is less than or equal to. So if we replace this inequality with this inequality, then the function f is convex. Then a function f is strictly concave or strictly convex if the relevant inequality is strict, that is, it's only greater than, not equal, or here less than, not equal to, then that will be strictly concave or strictly convex. The remark is that a function f is strictly concave if and only if the negative of the function is strictly convex. A linear function is both concave and convex. Function f is quasi-concave if for all x and y in the domain x and lambda in the interval 0 and 1 such that f of 1 minus lambda x plus lambda y is greater than or equal to minimum of f of x and f of y. A function is quasi-convex if the negative of the function is quasi-concave. F is strictly quasi-concave or strictly quasi-convex if the relevant inequality is strict. That is, in this case, if this inequality is strict, that is, there is no equal sign, this is only greater than, then that is a quasi-concave. If this is less than, strictly less than, then that will be quasi-convex. Ladies and gentlemen, this video explained convex, concave, quasi-concave and quasi-convex, strictly quasi-concave and strictly quasi-convex functions. Although these seem a little bit confusing and difficult, but they are not difficult at all. Kindly watch this video a number of times up to the end so that you could understand the concept. If you haven't yet subscribed to the channel, kindly subscribe to the channel and don't forget to click on the bell icon so that you could get regular notifications about my other videos that will be uploaded for you. Thanks for watching this video. Kindly subscribe to the channel and share various videos of this channel in various groups on social media so that this could reach you